All right, then let's get started. Welcome everybody to this week's award lecture. It's my pleasure to introduce our speaker, which is Christian Cyron from the Technische Universität in München. And just to give you a little overview on his CV. So Christian studied mechanical engineering at the same university, and he graduated in 2007 with an MS. And he did his MS thesis at Caltech with Michael Ortiz on maximum entropy approximation schemes. Then he returned to TUM to do his PhD with Wolfgang Wall. This is the leading group in computational mechanics in Germany. And he graduated in 2011. And after that, he went to France and did a postdoc at Polytechnique with Jean-Jacques Marigot, where he worked on variational methods in fraction mechanics. And in 2012, he moved further to the US, where he did a postdoc at Yale University with Jay Humphrey. And he left Yale because he won a $2 million package from the German National Science Foundation to work over the next 5 years on the mathematical foundations of growth and remodeling in vascular mechanics. And this is also where his current talk is on. So without giving more details, I welcome you again, Christian. And I'm looking forward to your talk, please.
Yeah, thank you very much for the kind introduction. It's a great pleasure and honor for me to be here, and I had already fairly interesting academic discussions the whole day long, and I'm looking forward for the discussions later in the afternoon. My talk will be about the theory of mechanobiological stability, which I developed over the last 2 years with Jay Humphrey. And in fact, I could have chosen it as an alternative title on behalf of the upcoming 150th anniversary of Davis Law in 2017. For those of you who are not familiar with this Davis Law, there was a surgeon here in the US, Henry Gassett Davis, and he published in 1867 a book called Conservative Surgery. And it wasn't paid much attention to back then, but later on it probably turned out to be one of the landmarks in biomechanics, one can say. And for those of you who are not familiar with Henry Gassett Davis' work, I'm briefly introducing this law because it is so important to understand biomechanics and growth and remodeling. So that's the motivation for my talk. I'm going to talk about growth and remodeling in soft tissue. And one has to distinguish two kinds of growth and remodeling. The first one is morphogenesis. That's practically what happens in an embryo or a small child, so if the organs are growing into their final shape. This is very much under the control of hormones and of biochemistry, also a couple of other factors, but hormones and biochemistry is really very dominant there. So that's here when the heart is growing into its final shape. And the interesting thing is, when you're adult, growth and remodeling doesn't stop. So even in adult tissue, you have growth and remodeling, but then it's mainly governed by what we call mechanobiology, but an intimate interplay between mechanical stimuli and biological processes. And a simple example would be your blood vessels. So for example, if in your arteries the blood pressure rises permanently, if you have hypertension, for example, if you eat too much of a salty diet, then the blood pressure rises. And the interesting thing is also the walls of your blood vessel become thicker so as to adapt to the increased blood pressure, so that the Cauchy stress in the walls remains pretty much the same. So the walls feel the increased blood pressure and then adapt to the higher blood pressure by higher wall thickness. And the question is, what is the rationale behind this? And the first person who understood this, at least in a qualitative way, was Henry Gassett Davis, and he formulated Davis' law. He said, well, he looked primarily at tendons, and he said, if soft tissue, if you put it under an increased level of tension, it elongates and it adds mass. And if you relax it, it gets shorter and it loses mass. So Davis' law comes down practically from a mechanical or more mathematical perspective to two postulates. The first one is there exists some kind of homeostatic stress state. And if tissue is kept in this stress state, nothing is happening. Then the tissue is happy. But if you perturb the stress state, if you, for example, put it under a higher stress, then it will elongate and it will add additional mass. If you put it under lower stress, it will shorten and it will lose mass. So the perturbation of the homeostatic stress always causes some growth and remodeling. That's practically Davis' law. And it's omnipresent in soft tissue. So what you see here is the tendon of a rat. That's a healthy rat, and this is a rat where you put one of the legs into a plaster cast for a couple of weeks. And what you see here is the density here of the collagen fibers is way lower. The rat lost over the weeks significantly mass. And actually you observe similar things, for example, if a man goes to space and comes back, there was no gravity, but there was no load, so the bones become thinner. So no load, no mass. That's the rule of how growth and remodeling works in living tissue. So Davis' law applies to atrophy and disused tendons. It also applies to thickening in arteries. So if you have more load, higher pressure, then you get more soft tissue in your walls. And it actually applies also to a couple of, actually to nearly all other forms of soft tissue. And the open question is now, what is the theoretical foundation of Davis' law? I mean, people have known it now for 1.5 centuries, and they have based their computational mathematical models on it. But still the question is, what is the rationale behind it? Why does it apply so universally to so many forms of soft tissue? The next question is then, if you understand the mathematical and mechanical foundations, how can we generalize this law? And then perhaps understand what we couldn't understand yet. So, and why are we interested in generalizing it and understanding more things? Well, the problem is very often growth and remodeling just helps you to adapt to a changing mechanical environment. For example, your tendon is under higher load, so it gets more mass, it gets more resistant. But the problem is sometimes growth and remodeling doesn't work as it should. One prominent example would be tortuosity. What you see here is an MRI image of your aorta. So the aorta is your most important blood vessel running down from the heart towards your legs and then splitting up into the two iliac arteries in your two legs. And these blood vessels should be more or less straight in a healthy person. And what you see here is the same person a couple of months later, and you see they're tortuous. That doesn't look quite healthy. And in fact, this is kind of an irreversible pathological form of growth and remodeling. The tissue has grown, for whatever reason, into a shape in which it shouldn't be. And while tortuosity itself is, it looks strange, but it is at least not overly dangerous. But there's another form of pathological growth and remodeling which is highly dangerous, and this is aneurysms. So this is again the aorta, your most important blood vessel, approximately as thick as your thumb. And it should maintain its diameter during your whole lifetime, more or less on a constant level. And in most people it does, but the problem is in a surprisingly large number of people it doesn't. So around 5 to 10% of the general population, that's quite a bit, develop at an age of around 60 what we call an aneurysm. So locally in one region, your aorta starts bulging out, so the diameter starts growing, and it keeps growing and growing in an uncontrolled manner, and at some point it may rupture, and it typically kills the people because the aorta is just your most important blood vessel. It's under extremely high blood pressure. If it ruptures all of a sudden, you typically die before you reach a hospital. And so this is actually the 13th leading cause of death in the US, for example. And this is why we are so interested in understanding the foundations of growth and remodeling, because if we can understand them, we can understand why sometimes it doesn't work, and then we can come up with new therapies. And of course, people tried to understand aneurysms already for decades. So the first thing which people tried was they tried to understand it on the basis of a blowout instability. But this was rejected because arteries compose of collagen. Collagen is a highly strained stiffening material. There, a blowout instability isn't overly likely. And then people thought, well, I mean, the arteries are under pulsatile blood pressure load. Maybe it's a dynamic instability. It's some kind of resonance phenomenon, but the problem is we have just too much friction, too much viscosity in the system. This hypothesis was rejected too. And that puts us into the strange situation that people have been working now for decades on aneurysms, one of the most important sources of mortality and morbidity in industrialized countries. And while we know a lot about the details of aneurysms, we still haven't understood the rationale behind them. And that's what I try to address with this theory. Try, of course, only, because we can't know yet whether this is really the answer. So the point where we started is we tried to explore the mathematical and mechanical foundations of Davis' law. And to this end, we first have to understand what is the difference between living tissue and an engineering material. So if you look here at this tractor tire or at this carotid artery, and if you look at both materials on the microscale, both look fairly similar. It's kind of a wavy polymer network. Of course, there are details, there are differences in the details in these networks, but at the first glance, they look surprisingly similar. And nevertheless, there is an important difference which we can realize only if you look at time. So over time, the fibers here remain more or less constant. They remain in the tire for the whole lifetime. There may be some minor chemical rearrangement or dissolution processes, but more or less it remains like that. And in living tissue, you have, by contrast, a continuous mass turnover. So in living tissue, there are cells like fibroblasts or smooth muscle cells, and they are migrating through the tissue and chemically dissolving fibers and replacing them by new fibers. So the fibers, and actually the average lifetime of a fiber is around 100 days. So the fibers which are now in my aorta won't be there probably in 3 months more. So turnover distinguishes this mass turnover. Old material is always replaced by new material, all the time. This mass turnover distinguishes living tissue from typical engineering materials. And the problem, why does it exist? Well, it's probably some kind of repair mechanism. I mean, our arteries are just subject to an enormous number of load cycles, around 1 million load cycles per month. So if you want to keep your arteries in shape for 40 or 70 years, you need to continuously repair them. And that's probably what this mass turnover is good for. So mass turnover in mathematical modeling of biomechanics is just often neglected. If you go to World Congress of Computational Mechanics, look at the presentation in biomechanics, people just say, well, we model biomaterials with a strain energy function as we would do for a polymer material, and that's it. And the problem is that's a good first approach, but it neglects this important aspect. And the question is now, is such a simplification of biomechanical modeling appropriate at all? And that's what we wanted to look at when we started with our theory. And to understand whether it's appropriate or not, let's just look a bit further at this carotid artery. So, and for simplicity, just to understand the concept along which we want to work, let's just look here at the fibers in one direction. And these fibers can be imagined as elastic springs, of course, under some Cauchy stress sigma. What happens now during mass turnover is you remove one of these fibers and you replace it by a new fiber. And this new fiber is integrated into the existing polymer matrix. And you can integrate it with any kind of pre-stress compared to the current configuration. So this pre-stress may be sigma pre. And now imagine the pre-stress by which it is integrated is smaller than the current stress sigma. What happens then is that the internal forces drop while the external loading remains constant. And then in order to rebalance the system, you need to dilate it. And if you degrade the next fiber and again replace it by a fiber of the same shape but a lower stress, the system will again dilate to rebalance. So what you see is we have a behavior which looks almost like a viscoelastic fluid going on here, only due to mass turnover. The question is now, how can we formalize this mathematically in higher dimensions? I don't want to bore you. I won't bore you with all the details which you can look up in the papers which we have published, but it's practically the theory of viscoelasticity which we're applying. We can just write mass turnover in the form of such a Volterra equation, and we can do similar things also in the nonlinear case. And what is important is actually more the result. We get here a stress relaxation equation, and this stress relaxation equation can be illustrated in a very simple way. This stress relaxation equation tells us that soft tissue behaves exactly like this mechanical analog model. This mechanical analog model has here a damper, it has here a spring, and it has here something which we call a motor element. And the motor element is just an element which is pulling inwards on this lower branch with a constant pre-stress sigma. So you can just imagine this is a force which is contractile and constant over time. So our calculus now shows that this is the mechanical analog model to understand a material which is subject to mass turnover. And this means that living soft tissue does in fact not behave really like a solid, as most people tend to think and tend to model it, but it rather behaves like a motor-reinforced viscoelastic fluid. And the time constant of this damper is around 70 days. That's the time constant of the mass turnover. So if you're looking at a much faster time scale, for example, at arteries during a cardiac cycle, you can just say the damper is rigid, and then you can just model it as an elastic material, no problem. But for clinical applications, you're often interested in the long time scale. Maybe you're performing a surgical procedure, and then you're not only interested what your patient looks like a minute after the procedure, but you want to know what happens a month or a year after the procedure. And then you can just not neglect this any longer. Also, so far, it's mostly neglected in modeling. So what are now the mathematical consequences of mass turnover? The first interesting thing is, if you look at this system, the upper branch is a fluid. It has this damper. So as soon as there is a load on the upper branch, the system will start dilating. Which means that in a static state, sigma has to be equal to sigma pre, because only then the upper branch is really load-free. So we know that there has to exist in the mass turnover in living tissue a deposition pre-stress, which equals the current stress of the tissue in a static state. And this actually explains why residual stress is so omnipresent in soft tissue. If you talk to biomechanicians, they're always talking about pre-stress, about residual stresses, and it has long been questions why this phenomenon is so omnipresent here. Maybe the answer, living tissue cannot exist without pre-stress because it could never maintain a static state because it needs some mass turnover for continuous repair. The question is now, so pre-stress is obviously necessary in living tissue, and the question is what governs its magnitude? And to understand this, we can say mass turnover causes an energetic cost, of course. You need to degrade fibers and you need to replace them by new fibers. And chemically, that causes an energetic cost proportional to the mass which you're turning over per unit time. But then you have a second cost, and that's the mechanical cost, because you're not only dissolving old fibers and depositing new fibers, you're also pre-stressing the new fibers. And that gives you an energetic cost proportional to the mass you're turning over and proportional to the strain energy for pre-stressing. So the size, the strain energy for a given pre-stress sigma pre. So mechanical design of your organs always pursues some objective function. So maybe it's some form of stiffness which you want to achieve, some stability under some pressure. You always have some objective function which you just can call in general some function f, which depends on the mass which you're willing to invest and which depends on the pre-stress which you're willing to invest. And if you then say, well, the organ has to fulfill a certain function in your body, then f is given. And then if f is given, if there's an objective value given, f defines your relation between sigma pre, the pre-stress, and the mass of the organ. And then here the energetic cost was originally a function of both, of pre-stress and of mass. Now by the objective function you can eliminate one of the two, and what remains is the energetic cost purely as a function of pre-stress. And if you plot it, it looks, for example, like this here. And what you see here is there's an optimum. And this optimum, it depends a bit on how you choose the parameters exactly, but the optimum lies always around approximately 150 kilopascal. And if you now ask a biomechanician who has done some animal experiments and tested what is the pre-stress in an arterial wall, he will tell you, well, something between 100 and 200 kilopascal. So here we have a rationale to understand the magnitude of the pre-stress in living tissue. It's simply a result of energetic optimization. So now the next interesting thing is we have understood there needs to be pre-stress, and we have understood what governs its magnitude. And the question is now, there's another omnipresent phenomenon in soft tissue, and that's mechanobiology. So if you perturb a system mechanically, there will be some response in terms of growth and remodeling. And the question is, why are biological systems so extremely sensitive to perturbations of the mechanical state? And interestingly, the simple mechanical analog model can answer also this question. The answer is, well, just imagine we are in an equilibrium state. Sigma equals sigma pre. Then the upper branch is load-free, which needs to be in a static state. So now imagine the external load increases. Then the Cauchy stress sigma increases. And then you have all of a sudden a load on the upper branch. And then your system will start dilating. Your soft tissue will start expanding. So how can you then restore again a static state? There are only two things you can do. Either you make the motor element stronger. Then you can again make sure that despite the higher sigma, all the load is supported by the lower branch. Then you're in a static state again. So that's one way to react. And the other way is you increase the tissue mass. If you increase the tissue mass, you increase the load-bearing cross-section. And then, even if the external load has increased, you may again reattain the same level of Cauchy stress, and then sigma equals again sigma pre. So to a perturbation of loading, your living tissue can react only in two ways. Either it increases its pre-stress or it increases its mass. But what it is most important, it has to do one of these two things. So any living tissue which wants to maintain a stable equilibrium state needs the capacity to sense changes in external loading and react accordingly by adaptation of pre-stress or mass. So we can mathematically prove here mechanosensing. And mechanosensing, that's an omnipresent phenomenon. Biologists have asked the question for decades, why does mechanosensing exist in practically all kinds of living tissue? And here we have, interestingly, the mathematical answer. The mathematical answer is otherwise stability would be impossible. So now we have reached the point where we can set up the mathematical foundations of Davis' law. So Davis' law practically came down to the assumption that there exists a homeostatic stress state, and if you perturb it, growth and remodeling starts. That was Davis' law practically, which he formulated 150 years ago. And now we can, for the first time, disclose the mathematical and mechanical foundations. We know there's fatigue and damage as a permanent problem in living tissue. We know, therefore, we need mass turnover as a repair mechanism, and we need mass turnover. We know mass turnover makes your soft tissue behave like a motor-reinforced viscoelastic fluid, and we know that this forces the soft tissue to have a pre-stress and to have mechanosensing. So these things are just a logical consequence of damage and fatigue. And then we know we are all subject to biological evolution, and biological evolution has optimized our body energetically. And we know there is one energetically optimal pre-stress. So there has to be pre-stress, and there is one energetically optimal value. And here we go. That's the homeostatic stress state which Davis postulated 150 years ago. And then we know if there is mechanosensing, so a perturbation of the homeostatic stress has then to be responded either by growth or by remodeling or by both. So here we have now understood that Davis' law is just a natural consequence of the presence of fatigue and damage and of the presence of energetic optimization in biological evolution. We have now understood the foundations of Davis' law, and the question is, Henry Gasset Davis was a brilliant man, but he was a medical doctor, and he was not a mathematician, he wasn't a mechanical or civil engineer. He didn't know much about mechanics. The question is now, he was nevertheless able to formulate this brilliant law, and the question is, what else could he have recognized and understood if he had known mathematics and modern mechanics? And that's what I'm going to address in my next talk. What could Henry Gasset Davis known if he had known variational calculus and functional analysis? So, and that's what we call the theory of mechanobiological stability. Just look again at this mechanical analog model. That's soft tissue. And now imagine you have a perturbation of the load. So then sigma is greater than sigma pre. So then a viscous dilatation of the body starts because you have all of a sudden a load on the upper branch. Then your damper is under load and it starts dilating. And then the problem is if your body starts dilating, you have a transverse contraction, of course, because soft tissue is more or less incompressible. You have a transverse contraction. Then your cross-section decreases over time. And if your cross-section decreases over time, the external load remains the same. Your stress will even keep increasing. So this means if you perturb your stress only by a little bit, by an epsilon, you start a process which keeps decreasing the cross-section and keeps increasing the stress until it ruptures. So every soft tissue is subject to a form of instability which is unknown in engineering materials. And this form of instability has absolutely been ignored so far. So and this is what we call mechanobiological instability. And the question is now, how can we avoid it? How can we keep living tissue as stable as an engineering material despite these unfavorable consequences of mass turnover, while mass turnover is necessary to repair damage? Well, the answer is, let's look at the same scenario. We perturb our state with, again, a transverse contraction. In order to keep our stress stable and make it return to the original homeostatic value instead of keep increasing, we need to prevent our cross-section from decreasing. So in this we can do by growth, because if we have growth, if we have more mass, we can, despite a transverse contraction, if the growth is strong enough, effectively overall increase the cross-section. So growth can change this here into this here. And then the stress will not increase over time, but decrease back to the homeostatic level. So if you have a sufficiently strong growth controlled by a mechanical stimulus, by an increase of stress, then you can always reattain a stable equilibrium state after perturbation. And that's then what we call mechanobiological stability. That's what your living soft tissue should behave like, because you don't want to flow away like a fluid. So altogether, this means that any mechanical body subject to mass turnover is potentially subject to a loss of geometric integrity and even infinitesimal load perturbations. It's a form of instability. And to maintain the geometric integrity, one has not only to satisfy the condition of mechanical stability, no buckling and such things, but there's a second hidden stability condition, which has largely been ignored so far, and we call this the condition of mechanobiological stability. And mechanobiological stability requires a capacity for a sufficient mechano-regulated adaptation after a perturbation. And the question is now, how can we formalize these simple intuitive mechanical and mathematical ideas? Well, to formalize it took us 2 papers and around 50 pages. We developed this theory largely along the lines of the variational approach to fracture mechanics put forward by Jean-Jacques Marigot, Gilles Francfort, and Blaise Bourdin a couple of years ago. It's in fact the problem is interestingly fairly similar to the problem of crack initiation in a slab which is cooling down. It doesn't look like this, but mathematically it's not so different, interestingly. And so we just set up we just used the typical framework of nonlinear continuum mechanics. And the only major change we have to do is we do not only have to look at the position of our material points, small x, but we also have to look at the mass density, which can change by growth and remodeling, so, which means that we have to introduce a generalized mechanobiological state vector composing of the position and the mass density. And then we can generalize the notion of a static state and say, well, static state does not only mean that the body isn't moving, it also means that it is not growing. So not only x dot equals 0, but also raw 0 dot equals 0. And then we have somehow to examine whether such an equilibrium state is stable. And this we can do on the basis of Lyapunov's stability theory, which you all, of course, know from control engineering and cybernetics. Well, maybe too many civil engineers here, but maybe some have also taken classes or worked in this field. So, well, what we are doing is Lyapunov's first method. We are linearizing practically around an equilibrium point. And in the end, we arrive at what we call the theorem of mechanobiological stability. And this theorem tells us that a system, a living tissue, is stable only if 2 conditions are satisfied. The first one is mechanical stability. Of course, I mean, if your system is buckling, then of course stability is not given. Then we have a second stability condition, and for this we can derive a linear operator, and only if all its controllable eigenvalues are positive, then the system is really immune against unstable growth processes. Which means again that living tissue is subject to a hidden stability condition, and the question is now, what happens if this stability condition is violated? And well, we just try to understand this on the basis of a simple model system. This here is a model for your aorta. So your aorta can be modeled in a first approximation by a circular cylindrical membrane. And now we choose on the left-hand side, we choose the parameters of the system such that all eigenvalues of this operator L were positive. And we perturb the system by removing a little bit of mass in the center, or by increasing the blood pressure. It doesn't matter, it has the same result. And what happens was nothing. The system is stable. If you perturb a little bit, it just returns to the original state or close to it. And then we chose the growth and remodeling parameters such that here we had 1 or more negative eigenvalues. And what happened after only an infinitesimal perturbation was this here. The circular cylindrical membrane started bulging out in the center, and this looks pretty much like an aneurysm. This is what an aneurysm looks like. And the timescale on which this here is happening, that's a couple of months or years, depending on the turnover in a certain individual. So this looks pretty much like an aneurysm, which makes it plausible that aneurysms might in fact be mechanobiological instabilities. And the question is now, how can we confirm this hypothesis? And to confirm it, we thought, well, it might be a good idea to use again mathematics, because the nice thing of our theory is we can derive fairly general propositions. We can derive propositions which parameters in the system should increase mechanobiological stability and decrease it. And if aneurysms are really mechanobiological instabilities, we would expect that the parameters for which we can prove that they decrease the mechanobiological stability, these parameters should be found to be especially pronounced in individuals with aneurysms. And the nice thing is this was the case. For example, there are experimental studies which confirm that in individuals with aneurysms, you have a faster turnover of collagen fibers than in the general population. And interestingly, we can prove that mechanobiological stability increases monotonically with the mass turnover time. So a faster turnover means lower stability, means that you're more susceptible to aneurysms. So we have here very good agreement between what we can demonstrate mathematically and what has been found experimentally. Then the next thing which we can demonstrate mathematically on the basis of our theory is that you are less susceptible to aneurysms if you have stiffer arteries. You may have other health problems like hypertension or so on, or high pulse pressure, but you're less susceptible to aneurysms. Now the question is this true clinically? And the nice thing is, the big problem is here really, old people have often quite stiff arteries, but they are also susceptible to aneurysms, but this doesn't mean anything because they have also other subtle biochemical changes. So we needed to look at a case where really only the stiffness was different from the general population and not the age or anything else. This example we found in diabetes. So people with diabetes may have a lot of health problems, but they have stiffer arteries, and they were also found to be less susceptible to aneurysms. So it has also its advantages to have diabetes. And the interesting thing is we can prove mathematically that higher stiffness should also increase the mechanobiological stability. So again, a very good agreement between what was found clinically and what our theory would predict. And then the last proposition is our theory predicts that mechanobiological stability should increase if your system is more sensitive towards perturbations of loading. So if you perturb the load by a little bit and then your system reacts by a very strong growth response, this should make you more stable. And this could be mimicked in an experiment by McDowell and co-workers in 2012. What they did was, for a given load state, they increased the collagen production by an inhibition of the microRNA 29B in mice. And these mice had previously been manipulated in such a way that they developed aneurysms. And what they observed was, after this manipulation, the growth of the aneurysms in the mice was much slower or even stagnated. So again, a perfect agreement between what our theory would predict and between what has been found experimentally by manipulation on a molecular level. Of course, we confirmed our theoretical results also by numerical simulations and found very reasonable results in very good agreement with everything which had been predicted and found clinically and experimentally before. I jumped to the conclusion. So in the first part of my talk, I had tried to set up the mathematical foundations of Davis' law. And the rationale was that we can understand Davis' law as a natural consequence of fatigue and damage, which we need to repair by mass turnover, and energetic optimization of soft tissue mass turnover. And the second part of the talk was about the question, what could Henry Gassett Davis known if he had known more mathematics, and so if he had known variational calculus, functional analysis, Lyapunov stability theory. And we believe that he could have generalized his law in the following way. He could have understood that soft tissue is subject to a hidden stability condition, and if this condition is violated, it is subject to a creeping loss of geometric integrity. And the nice thing is now, so we can even say exactly which factors are promoting this instability, and it's low mass production, it's low stiffness, and it's low half-life time. This might be the potential key to understand the enlargement of aneurysms. And if this theory turns really out to describe the rationale governing aneurysmal enlargement, then it could form the basis for future therapies against aneurysms, because so far there's no pharmacological therapy. You need to undergo a surgical procedure if your aneurysm gets life-threatening. And this might be the starting point to develop future pharmacological therapies. And interestingly, only a couple of weeks I was contacted by a clinician from Spain, and he had already set a starting point. So he had done a very interesting experiment which he hadn't understood. He had injected into the mice a crosslinker molecule, which is called lysyl oxidase. And what he realized was the aneurysms grew way more slowly. So, and then he wondered, might that be a key to find future therapies? And he didn't understand why they grew more slowly. And then he contacted me because he had seen my papers. And the nice thing was the theory could readily explain what was happening, because we know that lysyl oxidase is a cross-linker molecule, which is in fact improving the cross-linking between collagen fibers. So it makes the collagen tissue stiffer, and this theory exactly predicts that this higher stiffness protects you against aneurysmal growth. So we have already a first starting point along which we can hope that future development of therapies might work. But of course, the theory is pretty young, and we should really be careful and be very critical before we are too enthusiastic. I mean, we published it only a year ago, and it's not yet the time to be too optimistic, but rather to remain skeptical. Thank you for your attention.
Thank you very much, Christian, for your talk. And with this, I would like to open enough time for the discussion. Any questions? Okay, then I go first.
Christian, very nice talk. Thank you. Very interesting work. I want to go back to the constitutive relation, I guess, that you wrote down, or the dynamical system that you wrote down.
You mean the stress relaxation equation?
At the level of the Lyapunov stability relation.
Lyapunov stability?
Yeah. There we go. That looks like the one I was looking for. So, can you say a little bit more about how what's the dynamical evolution there for the mass, and what sort of
yes.
assumptions and things are coming in on the separation of timescales between mass
transport? Yes, absolutely. That's a very good question, a very important question. I skipped these details to save some time, but that's a very important question. So the point is, if you're interested in the mass evolution, we have a deposition rate of mass and we have a degradation rate of mass because we have turnover. And the point is, in general, both depend on stress or on other chemical factors, of course. And one of the simplest equations which you can write down is you can say, well, you may not know the exact relations, because there may be, I mean, in the nonlinear regime, far from homeostasis, that may be really difficult. But there's one thing which you can know. You know that in the homeostatic state, there should be a balance between degradation and between deposition of mass. And then you can prove, if you're only interested in stability, then in fact then you can assume that one of the two is constant and only the other depends on the stress, and you can say that it depends linearly on the difference between the current stress and the homeostatic stress. And this is actually without any limitation. The only underlying assumption is that both deposition and degradation of mass are continuous functions depending on the stress in the neighborhood of the homeostatic state. So the simplest way here to write down these equations is you could say the degradation rate is constant. You have just the Poisson process, which is degrading your fibers stochastically. And you can say the deposition rate is just exactly balancing this Poisson-like degradation in case that your stress equals the homeostatic stress. So if sigma equals the homeostatic stress, and if there's an increment delta sigma, you can just say that the mass production rate has an additional additive term of the type delta sigma times some factor k sigma. So that's the way how we model it. And that's pretty much the standard. I mean, if you look at the literature, there are different models how you model deposition and degradation of mass. But the nice thing is, around the homeostatic state, they all come down to this. Around the homeostatic state in this neighborhood, there's mathematically just no difference. That's the nice thing.
Okay, thank you. Maybe a quick second question.
Yes.
You motivated by a one-dimensional model, the behavior.
Yes.
Do you have any comments briefly on the anisotropic, how to extend that to anisotropy?
Yeah, so that's also a very important question. So one of the simplest way, I mean, growth and anisotropy, that's still a thing which is quite controversial. I mean, people are arguing a lot about these things. One of the simplest ways how you can deal with anisotropy here would be you take a fiber family model. So you say your collagen tissue consists of n families of collagen fibers in a given direction. And then you model growth and remodeling in each fiber family separately. This would be one simple approach how you can deal with anisotropy. There may, of course, be others, but that's the simplest approach. And that's also what we assumed when we produced the simulation here. But there may be other better ideas. I would say that's definitely one of the spots where future mathematical modeling can contribute a lot of improvements.
Like any model, your model must be based on some set of assumptions. And one of them, it seems to me, is that this degradation and replacement is not a parallel process, but sequential. That you first lose the fiber in order to replace it. Is that what you see also in practice, or that happens simultaneously? And then maybe this pre-stressing part of it may not be necessary if that happens at the same time.
Well, so what you have in practice, of course, you lose infinitesimal quantities of mass, and you replace it by infinitesimal quantities. But nevertheless, whether it happens simultaneously or in series, that should not change the problem of this dilatation, because what happens in the end is always you degrade a fiber which has in a certain configuration a stress sigma, and you replace it by a new fiber with a lower stress. And then you always need to stretch a bit more the tissue as a whole to rebalance the external load. So what we are assuming is it happens really on an incremental level, and we are saying at each point in time an infinitesimal mass increment, dm, is replaced by an infinitesimal mass increment of a lower stress. And this gives you the stress relaxation equation.
Thanks for a fascinating talk. I understand that the reaction to increasing stress is increasing mass, right?
Right.
Is the process, I think you mentioned it, but I'm not sure, is it reversible? So if the stress reduces, is the mass decreasing?
Yes, in general it is. So you, for example, I mean, one of the most prominent examples is if you're doing a lot of exercises, your bones, I mean, that's not soft tissue, but in bone it's in many respects similar. So your bones grow stronger, you have a higher density in the bone. And if you then stop doing exercises, you lose again bone mass density. Or, for example, if you go to space for a while and you don't have any load at all, you lose also density. And yeah, as far as we know, the process is reversible. Also, that's another question which is still kind of subject to a lot of examination. We are not quite sure whether when it is reverted, it's reverted exactly on the same path or on a slightly different path. So that's one of the things. We know that qualitatively it is, it can be reverted, but about the quantitative modeling, that's still something which we need to explore further. That's, I would say, subject of current research still, but in principle it works. It's reversible.
Yeah, so the background of my question really is if the body does something wrong, so it makes something too heavy, then it would be able to get back to the original state if you manage to reduce the stress.
Yeah, right. That would be an approach. Yeah, I mean, we had actually thought for a while whether it might help, for example, for aneurysms, if you could just reduce for a certain period the blood pressure, then you would unload it a bit, and then you might hope that it's kind of reverted. The problem is, so of course, before trying anything like that, it would be good examining carefully the literature, and we did so. And the big problem is, if you look at the literature, people have examining the relation between hypertension and aneurysms for decades. There was a recent paper, and the main conclusion is that nobody really knows what the relation is. So the problem is simply there are just a lot of other factors in every human being which might contribute, and it's really hard to isolate So we can right now simply not say whether decreasing the blood pressure would really help. Our theory would make us assume so, that this could help. The next thing is why we don't know it exactly. When people have aneurysms and they go to a medical doctor and he discovers them, they often get some drugs in order to downregulate the blood pressure. So most people in which aneurysms are regularly monitored actually do no longer have hypertension, but rather the blood pressure has been restored to the original level. And what makes things even more complicated is we know that these drugs restore the blood pressure back to the normal level, but they may also change in very subtle ways the microRNA processes on the microscopic tissue level and then affect growth and remodeling exactly in the opposite way. So in general, I would agree it would be a very nice idea to try this out, but there are also a lot of cofactors which have to be considered really carefully.
My question is it's almost a continuation of the previous one. So if you can you derive a certain load level pattern which either reduce or increase not level load pattern which increase stability. For example, if you cycle load, is there any frequency which accelerates instability or opposite decrease it, or static versus dynamic?
Yeah, in principle, we could imagine that there are there is an impact of dynamics here. Actually, we can be pretty sure because what we know is that it makes a difference physiologically whether you have a static loading or cyclic loading. We know this for sure for bone. We know it also for arteries to a certain extent. The big problem is we didn't include these effects into this model because there's just not enough known right now about how to quantify this effect. I mean, I'm personally pretty sure that dynamics plays a role. But in order to quantify it, we really need to come up with a rigorous mathematical hypothesis. And all studies which have been proposed to quantify this effect, well, at least I'm not aware of any, which I would consider already now a sufficient basis on which one can build up a rigorous mathematical theory. But I would say that's definitely one of the future avenues of research to explore the exact impact of dynamics, because that might also be easier feasible for a patient if we discover certain load patterns which can stabilize the system. It may be easier to arrive at such load patterns than permanently increase or decrease the blood pressure, because the load patterns you may influence, for example, by doing exercises or such things. So if one could discover anything like that, that might be interesting, and that would be a future avenue of research. But so far, the quantitative experimental data is just not yet sufficient to support mathematical developments, I would say. But that will certainly change over the next years, I hope.
One more. So back to the micromechanical model. I was just curious in the discussion that you had just a second ago. You talk about the model in terms of fibers, individual fibers coming into existence and leaving. But I'm sure at a very micro scale, they're being formed not as whole fibers. So can you say something more about the actual mechanisms and how and why then fibers would form with a particular pre-stress?
Yeah, that's also one of the big questions, I would say. So the problem is how can you monitor it? There are people who really try to observe this process optically by a microscope, but that's really hard, as you can imagine, on this length scale. I mean, that's kind of the length scale of a couple of micrometers in the end. I mean, the fibroblasts, you can, the diameter may be something like 40 micrometers, so it's really hard to observe it here by a microscope. And then other indirect indicators how this process are happening are also really hard to find. The current hypothesis is that the fibroblasts and the smooth muscle cells are producing the fibers, and they are synthesizing the fibers. And there is, as far as I know, so there's one group, I don't know where, but they are claiming that they really took a movie of how a fibroblast produced a fiber and then stressed it. And then the question is, how is it integrated into the matrix? And this probably happens by the expression of crosslinker molecules. I just mentioned this crosslinker lysyl oxidase on my very last slide. And many people are assuming that what cells may do, so nobody's really sure about it, but many people would assume that the cells are just producing a fiber and then maybe stressing it in some way, and then they are locking it into the matrix by expressing a huge amount of lysyl oxidase, which is a crosslinker, and then connects the fiber in the stress state to the already existing fibers. Because what we know is, how we can confirm this hypothesis, or at least check it a bit. We can prevent the fibroblasts from producing lysyl oxidase. And then we observe that there is no pre-stress any longer. And second, what we can do is we can prevent the fibroblasts from developing an internal stress in their cytoskeleton. Because, I mean, if in order to stress the collagen fibers, the fibroblasts need the capacity to develop some force. And we can suppress this by taking out the actin-myosin motor machine on the subcellular level, and this can be done too. And in this case, there is no pre-stress, there isn't any pre-stress either. So we know that probably when the fibers are stressed and built into the matrix, we know that it plays obviously a role that the fibroblasts have a cytoskeleton which can kind of pull on surrounding fibers, because if we suppress this capacity, there is no pre-stress any longer. And we are pretty sure that they are pulling and then kind of turning the stress they are exerting into a permanent state by expressing crosslinkers, which are kind of freezing the current deformation state. So that would be the current idea how we would imagine it. But I wouldn't claim that this is already the final way to understand it. But all these experiments, if you're interested, you can look it up in papers in tissue equivalence. One of the few ways how you can examine it is tissue equivalence. You can't examine it very well in vivo, but you can just take a tissue culture and you take, for example, a collagen disc and you seed it with fibroblasts. And then you can you can manipulate in detail certain intracellular processes. And this way, you can kind of answer these questions which you just asked. So the experiment is actually not even too hard to perform. So depending on your background, you just need a tissue culture, you need some basic knowledge of biochemistry and some basic knowledge of mechanics, and then you can do the experiment yourself, actually.
You mentioned at some point that it's being modeled with a nonlinear continuum mechanics model. So could you mention some theory that is being used to consider the growth of the tissues in that model?
Yeah, what we say is, so we model the artery, we model as a constrained mixture of elastin, of collagen, and of smooth muscle tissue. And the smooth muscle and the collagen fibers we model by, for example, by Fung exponential strain energy functions. That's a very common way, not the only way, but very common. And the elastin is commonly modeled by a neo-Hookean isotropic material. And then for the growth itself, we just say that at each point, we just say we look at the stress, at the current Cauchy stress in the collagen fibers. And if this current stress equals a homeostatic value, which we have to set up somehow, that's kind of an intrinsic control variable of the cell. If the current stress equals the homeostatic stress, then just as much mass is produced as degraded over time. And if there is a difference delta sigma, then we have a mass production proportional to this difference. That's how we are modeling it right now. But there's still certainly, it probably will be possible to come up with better models in the future. But the problem is always simply, I mean, people in biomechanics often propose very difficult models with many parameters, but many parameters don't serve for anything if you don't have experiments to support them. So our philosophy is really we only model things on the basis of mathematics to the extent to which we can strongly support it by experiments. Only what we can observe by experiments or what other people have observed by experiments we really would like to see in this theory. And other things we rather prefer to leave out rather than having a dozen of parameters where nobody really knows what they mean.
Time for one last question, if there's any. Okay, this is not the case, so let's thank the speaker again. And let's proceed to the reception. Thank you.